Hey guys, welcome to our second day of live from the Biosphere. We're closed to the public, but some of our research is continuing through our university shutdown, and we wanted to bring you behind the scenes and talk a little bit more about the in-depth science that we're doing and continuing in a limited fashion. Today we're in the underbelly of one of our flagship projects here called the Landscape Evolution Observatory. Now, this is the steel structure beneath what is an artificial landscape that represents a hill slope catchment system. Now, you can think of a hike in the Catalinas when you see a couple of faces converging and somewhere where water might start to form a rivulet or a stream. This is the kind of landscape that we're studying above us right now. And you won't be able to see it from this vantage point, but above us we've got about 300 square meters of basalt soil. Now, that basalt was mined from northern Arizona, from the Merriam crater, several years ago. And the idea was that we bring this volcanic soil into the biosphere, and this soil represents early stage evolutionary soil. So as we start to manipulate the climate, add rain and weathering, that soil, we believe, will start to change. And what we do at the Landscape Evolution Observatory is we monitor those changes very specifically with a high profile of sensors. Now I'm going to bring you guys up into the underbelly and show you some of our sensor networks and automated sampling systems to give you a sense of the kind of volume and density of our networks that we've created for these landscapes. So when you're ready, I'll try not to freak out our camera woman, and we'll head up. Ready?
Ready.
So now that we're much closer to the underbelly, so close we can touch it, I'll start with a little walkthrough of what we're looking at up here. We've got these tubes coming out of the soil, and at every point where there's a tube, there's a two-dimensional sensor profile. So we have stacked sensors. Now, you can think of sensors as including anything from something that measures temperature or soil moisture to something that measures the CO2 or physical water sample. You can see these different color tubes. We've got black and clear. The black tube, or the black lines, correspond to our electronic sensors, and the tubes correspond to gas and water. And that's where we're physically sampling gas and water from inside the landscape. Now, above me is about 1 meter deep of soil, and starting at about 80 centimeters in depth and going all the way up to the surface, we've got these sensors spread out all around the landscape. So think of this as a three-dimensional grid, and what we've done with a lot of these sensors is turn them into automated sampling systems. Because we have 3 landscapes like this, with a couple thousand sensors on each landscape, to physically take readings or take physical samples would be very tedious. So what we've done is gone ahead and designed automated systems that can do the sampling for us, which is great because it allows for higher volume sampling and a higher coverage and kind of representation of what we're seeing in the soil. Now, what we study in the soil primarily right now is hydrology and subsurface water flow. So when it rains, that rain falls into the soil, percolates into the ground, and starts to move in the path of least resistance. So as that water moves through the landscape, it's potentially choosing specific pathways. it's reacting with our soil and causing weathering. So we're monitoring these changes on a scale that kind of factors in the idea of a landscape evolving. So all the soil was the same compaction, the same material, chemical composition, but as these changes start to occur, we're going to see changes in the soil, in the geochemistry, and in the way that water moves through these systems. So, for example, one of the ways that we monitor geochemistry is that we actually, during a rain pulse above us, will use what's called a vacuum chamber to collect simultaneous water samples from all of the different points that we're monitoring within the soil simultaneously. So you can look down at our vacuum box here, and you can see all these tubes coming in from different XYZ coordinates in the soil. At the end of these tubes within the soil, we have these porous clay membranes that sit up right against the soil and pull water in through these very tiny pores. That water travels through these sensors into a vacuum chamber that we control the pressure using a compressor in our basement. So you can imagine all the air is getting sucked out of this chamber, and it's causing droplets of water to move into these systems and fill up our test tubes. So at the end of a sampling period, one of us will come up here in the scissor lift and pull our samples, and we'll bring those samples to the geochemistry lab for analysis. Now, when LEO was created, we wanted to add a sensor network that was going to last for at least 10 years. Now, when you're designing a 10-year project and you're comparing it to studies in the field, well, one of the common things that happens out in the field is that you've got sensors that die off. And once we added this sensor network into the soil, we knew that we didn't want to tamper with the environment because we're studying evolution and weathering. We didn't want to have to dig back into the soil, go back in and make changes or pull out sensors. So once things die off, we leave them be. What we've done is create this redundant sampling system, though, that has some resiliency to this sensor die-off. So if we lose a quarter of our sensors, we're still going to have a representation that gives us a really good look at the subsurface chemistry and hydrology of the entire slope. Now you can think of this landscape that's above us. It's about the size of a third of a football field, and it's on a 10-degree slope. So water is moving downslope in this and it's going to, follow gravity down to what we call the seepage phase. But during that travel period, we're studying things like, well, how long does it take the water to transport all the way down there? And what kind of biological, atmospheric, and kind of physical attributes lead to the change of that transit time. We call that transit time distribution. So as a scientist here on LEO, you kind of have to be a jack of all trades. You've got to be okay with heights and industrial climbing. You have to be good with working with electronics and sensors, and also designing new systems that make sampling and monitoring the evolution of this landscape much more simple. So that's about it from the underbelly of the Landscape Evolution Observatory. We want to wish you all a very safe next couple weeks as we're dealing with some unfortunate situations. But we'll be coming back to you tomorrow with continued science updates from the Biosphere and closer behind the scenes look at some of our research. Thank you so much. Wishing you well from the Biosphere.